So, in the last lecture we saw that LP mu, where P is between 1 and infinity, including 1 and infinity, is a complete metric space. Our next aim would be to look at finer properties of LP spaces. So, this is very similar to what we did when we constructed the Lebesgue measure earlier. We looked at finer properties of measurable sets, approximating it with compact sets, sets which are union of cubes and so on. So, this requires some extra structure on the space X, where the measure and the sigma algebra are existing. So, we will set that up and then prove some results which will be applicable also for Rn and the Lebesgue measure on Rn. Okay, so, let us start. So, let us recall first that we had x f mu and we have LP mu. This is a complete metric space for 1 less than to p less than or equal to infinity. Remember that we identified functions which are equal almost everywhere. Okay, so, the first thing you should observation or a theorem is that simple functions are dense in LP mu. So, you look at the class of simple functions, simple functions S, such that of course, it should be in LP first of all. So, we need it to be supported on a set which has measure finite. So, all those x in X such that the simple function takes the non-zero value, that should have finite measure, okay, because these are constants on various sets. So, if I have several sets on which it takes constants, and if they add up to, if the measures are infinite, then of course, this will not be in LP. That is why we need this. Okay. So, the class of simple function sets such that this is true is dense in LP, in LP of mu, and this is true for all p, okay, including infinity. So, that is important. Well, this proof is very simple because we already know how to do this. So, we start with as usual we separate out infinity case is trivial in this case, p less than infinity. Then we know that if I take f in LP of mu, f positive, then we know that there exist simple functions Sk increasing to f, right. These are positive simple functions increasing to f. So, Sk, each simple function is less than or equal to f. So, Sk would also be in LP, right, by monotonicity, and by dominated convergence theorem Sk will converge to. So, you can look at f minus Sk to the p. So, this is the LP norm of, right. So, this is the LP norm of f minus Sk, well, to the p, because I am not taking the 1 by p on the left hand side, and this will go to 0, right, because f minus Sk, I know f minus Sk goes to 0 almost everywhere, and modulus of f minus Sk, well, f is greater than Sk. So, this is actually f minus Sk itself is less than or equal to 2 times f, which is in LP, right, is in LP. So, apply dCt to show that this goes to 0 immediately. So, simple functions are dense. L infinity case I will leave it to you exercise, because we know that if the function is bounded, if f is bounded, we already know that Sk converges to f uniformly. Sk converges to f uniformly, which is the convergence in the L infinity norm. So, this is a trivial observation. So, there are simple functions. So, simple functions are dense. So, that is the upshot. But if x has more properties like locally compact Hausdorff spaces, right, T2 space, and we have measure mu and the sigma algebra M given by or as in Riesz representation theorem, as in RRT. Remember, RRT is the Riesz representation theorem, which gave us measures for positive linear functionals, Riesz representation theorem with certain properties, right. So, one should recall all these properties. Measure the sigma algebra M contained the Borel sigma algebra on X, and mu of compact sets was finite for every compact K, and we had outer regularity and inner regularity for some sets, right, inner regularity for sets with finite measure, So, these properties we had seen before. So, I am just recalling them. So, all these are true. If you have such a situation, then one can say more. Okay. So, aim is to show that continuous functions with compact support CCX is dense in LP, of mu. So, where mu is with all these properties coming from Riesz representation theorem, 1 less than equal to p, strictly less than infinity. Okay. Remember that p equal to infinity, it is not true unless extra properties are assumed on X and things like that, because of convergence being uniform and continuous uniform limit of continuous functions is continuous and so on. Okay. But before we get into proof of this, so this requires what is known as Lusin's theorem, which I will prove first. But let me comment upon what is meant by CCX is dense. So, CC of X is contained in LP of mu. So, first let me justify this. Well, what is there to justify? Because the right hand side, this is a collection of equivalence classes. So, remember that here we have equivalence classes, strictly speaking not individual functions, right, we look at equivalence classes. But this is a function space, it consists of functions, not equivalence classes. So, what do I mean by this containment? What is the meaning of this? Well, I take an f here in CC of X and I send it to the corresponding equivalence class. Okay, so, that is a map. Well, first of all, why does it go to LP mu? Because the support of f is compact. So, support of f is compact. So, if I look at integral over x mod f to the p d mu, well, this is equal to integral over support of f, because outside support of f is 0. So, mod f to the p d mu, and this is less than equal to, it is a bounded function. So, you can take the L infinity norm of f outside and you will have measure of the support of f, right. So, there is a power p here and this is finite, right. This is finite because this is compact and mu has this property that mu k is finite for compact sets. So, all functions in CCX are in LP. So, I can look at the corresponding equivalence class in LP. This is a 1-1 map, it is an injective map. Why is that? If I take two functions f and g in CCX, if the equivalence classes are same, so if equivalence class of f is same as equivalence class of g, this would imply f equal to g almost everywhere. Okay. So, now this is a easy exercise. So, let me write it here, exercise. If f and g are in CCX, well, you do not need CCX, continuity will do, f equal to g almost everywhere, then f is actually equal to g at all points for every x in x. Okay. So, the difference between almost everywhere and for every x is that in almost everywhere you are allowed a set of measure 0 where equality is not true. But when f and g are continuous, this does not happen, this almost everywhere becomes everywhere. So, that is why this map is injective. Okay. So, I can view CCX inside LP mu and I am claiming it is dense. Okay. So, for that we need Lusin's theorem first. Lusin's theorem. Okay. So, I will assume that X has the property X is locally compact T2 and I have the measure mu and the sigma algebra M as in Riesz representation theorem. So, this is the basic assumption on X. Okay. And we know that if X has more properties like sigma, compactness and so on, then we have more properties for mu and M and so on. Okay. Suppose F is a complex valued measurable function. So, I am assuming F to be finite at all points. So, F is finite for all x, it is not necessary, but you know we are trying to approximate this by continuous functions. F is a complex valued measurable function on x and there exists a set A in the sigma algebra such that measure of A is finite and f is 0 outside, okay, and f of x equal to 0 if x is not in A. So, f is supported on a set of finite measure. Okay, so, Lusin's theorem is for sets with finite measure. Suppose f is a complex valued measurable function on x and there exists A such that mu A is finite and f of x equal to 0 if x is not in A. For epsilon positive, there exists some function g which is continuous, right. Okay. So, mu A is finite is important, g is a continuous function is important such that the measure of the set where f is not equal to g. So, remember g is a continuous function and f was an arbitrary complex valued measurable function which is supported on a set which has finite measure. So, I can construct a continuous function g such that mu of x where f of x is not equal to g of x. So, look at the set where f is not equal to g that has measure less than epsilon. So, for any epsilon I can do this. So, I can reduce the epsilon as much as I want, right. So, I can approximate f by continuous functions, that is what it says. We may choose g so that supremum. So, this will be useful in applications supremum over x in x such that mod g x is less than or equal to supremum over x in x mod f x. So, you can choose g's to be bounded by the L infinity norm of f. So, that helps in taking limits and things like that. So, this is the first thing we want to prove and then we will choose epsilons a sequence going to 0 which will give us a sequence of continuous functions which will converge to f, and that is what proves that LP CCX is dense in LP. So, proof of this is divided into some cases. So, first assume that 0 less than or equal to f strictly less than 1, okay, and the set A is compact. So, all this is for simplification and we will go to general cases soon. So, let us assume, so keep the assumptions in mind, f is less than 1, A is compact. So, outside a compact set f is 0. Okay, so, we know that there is a sequence of symbol functions, right. So, we know that there exists Sn simple and of course, positive Sn increasing to f, right. So, this is one of the basic theorems we have done. Now, what you do is put, okay, so this is slightly technical. So, put T1 equal to S1. So, that is the first function, Tn equal to Sn minus Sn minus 1, okay, n greater than or equal to 2. So, remember each Sn was a simple function constructed in a certain way, right, by decomposing the range of f. So, remember that construction that will be needed. Then 2 to the n times Tn is a characteristic function of a set capital Tn, which is contained in A. Of course, A is the support of f, outside that everything is 0. Well, what does that mean? So, let us let's just recall the construction of Sn's. So, Sn's were constructed. So, f is between 0 and 1. Okay. However, Sn's constructed, remember the you divide the range of f. So, range of f here is 0 to 1. You divide this into 2 intervals first and then into 4 intervals and so on, right. Each time you divide each interval into 2 equal parts and choose the lowest endpoint for the value of Sn. So, if you go back to the construction, you will see that the value of Sn was always something like k minus 1 by 2 to the n, right, where f was between, f of x was between k minus 1 by 2 to the n and k by 2 to the n. This is how it looked like. So, if I look at one such interval, so let us say this is k minus 1 by 2 to the n and this is k by 2 to the n. Okay. In the next step, you divide this into equal parts and depending on f, where f falls, if f falls here, it is still this value, if f falls here, then the value increases to this, right. That is how we constructed the symbol functions. So, let's look at some simple example. So, the value of Sn's can be, it can be 0 by 2 to the n, 1 by 2 to the n, 2 by 2 to the n, 3 by 2 to the n, right, 4 by 2 to the n, etc. So, let us say this is where f falls. Then in one case we will have at Sn we will have value 3 by 2 to the n. Okay. Then this is divided, right. So, the interval 3 by 2 to the n to 4 by 2 to the n is divided into 2 parts. Okay. So, what is that? Well, this length would be 1 by 2 to the n plus 1. Okay. So, if you write it in terms of n plus 1, this is 6 by 2 to the n plus 1 and I have 8 by 2 to the n plus 1, these are the end points. So, the midpoint is 7 by 2 to the n plus 1. Okay. So, if f value falls here, it would be still 3 by 2 to the n, which is 6 by 2 to the n plus 1. If f value falls here, then the value of Sn increases, right. So, Sn plus 1 will be, so in this case Sn of x was 6 by 2 to the n plus 1 and Sn plus 1 of x would be 7 by 2 to the n plus 1. Okay. So, if I look at the difference of this, so the difference is 1 by 2 to the n plus 1, right. And so, if I multiply this by 2 to the n plus 1, I am going to get 1 in that interval, which is the characteristic function. So, 2 to the n into Tn, Tn is the difference, right. Here I multiplied by, here I was looking at Sn plus 1. So, I am looking at Sn plus 1 minus Sn into 2 to the n plus 1. Okay. So, this is characteristic function of something, right, that is what is written here. If Tn is this, I multiply it with 2 to the n, then it is the characteristic function of a set. That is how these Sn's are constructed. Okay. So, we use that. Okay. So, let me rewrite. I have Sn increasing to f, I called S1 to be T1, then Tn was defined to be Sn minus Sn minus 1. The interesting property of Tn is that if I multiply Tn, the function, by 2 to the n, this is a characteristic function of some set Tn, which is contained in A. A is where f is supported, right. Now, this we can rewrite as f of x equal to summation T n x, n equal to 1 to infinity T n of x belonging to x, right, because this is a telescopic sum, we have seen that. So, when you keep adding, all the terms get cancelled except the last term, which gives me the limit of f, limit of S n. Okay, so, we have written down f in terms of T n's. T n's have the property that this is indicator of a or characteristic function of some capital T n, which is a set contained in A. A, remember, was compact. Now, fix an open set V such that V closure is compact and A is contained in V, right. That is possible because A is compact. So, I can take a slightly bigger open set which contains A and whose closure is compact. So, all this is properties of locally compact Hausdorff spaces. Okay. So, now we construct several compact sets and continuous functions. So, then there are compact sets K n, open sets V n such that K n is contained in T n, contained in V n, V n's are open sets contained in V. Okay. So, this is compact, these are open. Okay. So, remember V is contained in V closure, which is compact. Okay. So, again all these are properties of locally compact Hausdorff spaces, we have seen this. Well, not just that, measure of V n minus K n is less than 2 to the minus n epsilon. So, epsilon, remember, is given to us, we are trying to get a continuous function which equals our function except on a set of measure epsilon. So, all these properties come from Riesz representation theorem, right. So, we have this. So, now by Urey-Schwan's lemma we can construct continuous functions. So, by Urey-Schwan's lemma there exist continuous functions H n which are continuous functions with compact support. So, and they are between 0 and 1 such that indicator of K n is less than or equal to H n, less than or equal to indicator of V n, right. So, in other words, H n equal to 1 on K n, 0 outside V n, right. So, given a compact set and an open set containing that, we can do this, and that is precisely Urey-Schwan's lemma. Okay. So, use this H n to construct. So, T n is between K n and V n, right. So, I have K n's here, I have T n's here, and I have V n here, right. So, that is how it looks like, and H n will be 1 here, 0 here. So, it is very close to T n, it is very close to the indicator function of T n, and we are trying to sum up T n's, right, that is my function. So, define, all that you have to do is to define a continuous function g of x to be equal to summation n equal to 1 to infinity 2 to the minus n times h n x. Well, what is the 2 to the minus n doing here? So, recall that 2 to the n times T n is a characteristic function. Okay. So, that is what is 1 in T n, but T n. So, if you look at this, the K n's are smaller than T n, but my functions H n's are 1 there. So, if I multiply by 2 to the minus n, it would be like S n minus 1, which will approximate f. That is what I want to do. Okay. But recall H n's are less than or equal to 1 when between 0 and 1, and so this converges uniformly. Hence, this series converges uniformly. But these are continuous functions, right. It converges uniformly because HNs are less than or equal to 1. So, use Weierstrass M test, right. So, this but HNs are continuous and the series converges uniformly. So, this would imply G is continuous and G is of course compactly supported, right, because everything is supported inside V. Okay. So, support of G is contained in the fixed open set V, right. So, remember V is one open set which is fixed, okay, and all the Kns and Tn Vn's are all contained in V and V closure is compact. Okay. So, support of G is contained in V. So, G is a continuous function with compact support. Well, not just that, if you look at 2 to the minus n times Hnx, well, this is Tnx except in Vn minus Kn, right. Look at this picture again. So, on Kn my function is 1, on Tn my function Tn is 1. So, 2 to the minus n times Hnx equal to Tnx inside at least here in Kn, right. So, it will not be true outside Kn, which is this set, but this set has measure small, Vn minus Kn has measure less than or equal to 2 to the minus n times epsilon. So, when I look at this expression, for each term I have this set where they are not equal. So, when I add up, I take the union of all those sets and outside that we have equality, right. So, convince yourself that we have g of x equal to f of x, right, because f of x was summation Tn, that is the reason, right, f of x except in union of Vn minus Kn, right, which comes from here. But what is the measure of this? Measure of union n Vn minus Kn is less than summation 2 to the minus n epsilon, which is less than or equal to epsilon. So, outside a set of measure epsilon, I have g equal to f. Remember, f was one function we started with, which was between 0 and 1, and f was supported on compact set. We constructed a continuous function which equals f almost everywhere, except on a set less than epsilon. So, we finished the case. 0 less than or equal to f strictly less than 1, A compact. Okay. So, same proof works for f bounded and A compact, right, because from bounded you can go to less than 1 by dividing by a constant and you can approximate it by continuous function. Okay. So, next assume measure of A is finite. So, in this case A need not be compact, okay, but f bounded. So, that is also fine because I can reduce everything to compact case by approximating A by a compact set. So, this follows because for every epsilon positive there exists a compact set K contained in A such that measure of A minus K is less than epsilon, right, and on K I can approximate f by CCX functions, that will do, right. Okay. So, we have finished off the case when f is bounded and mu of A is finite. Okay. So, if well, so remember this is a property, this is the inner regularity property of the measure. Okay. So, if f is not bounded, next if f is not bounded, well we modify it, okay. So, let B n equal to, so slight technical point here, is greater than n. So, you look at the set where f is greater than n, mod f is greater than n, then B n's are decreasing, of course, B n's decrease, and B n's decrease to the empty set, right, because f is not taking the value infinity, and so mu of B n will go to 0. Remember, because all these are contained in A, because outside that A is f is 0 and mu of A is finite, that is our assumption. So, on a set of finite measure we have these things, and so mu of B n will go to 0. Okay. So, since f coincides with 1 minus chi B n times f except on B n, above proof will work, right, above proof works, because outside what is chi minus B n, 1 minus chi B n will be 0 on B n. So, this is nothing but f of x when x is in B n complement and 0 when x is in B n, and on B n complement mod f is less than or equal to n. So, that is a bounded function, and this f can be approximated on B n complement by continuous functions with compact support, right. So, you take n large enough, mu B n will be less than epsilon by 2, approximate f by continuous functions up to epsilon by 2, and you have the result. Okay. So, let me complete this proof by, so we had one more assertion here, we can arrange it so that the boundedness of the bound of G is given by bound of f, right, the L infinity norm of G bounded by L infinity norm of f. So, that is easy, that is just rewriting whatever we have just seen in an appropriate manner. So, let us just finish that by saying this. So, finally let R equal to supremum of mod f x, x and x. So, you take the L infinity norm of f and define. So, we are just modifying our G. Okay. So, for this first define phi of z to be z if mod z is less than or equal to r. So, this is in the complex plane. Okay. So, r z by mod z if mod z is greater than r, and look at, so phi, what is phi? Phi is a continuous function. So, this is a continuous function from the complex plane to ball of radius 0 with ball centered at 0 with radius r, right. So, if G is the function which approximates f as above, we do not know where G is bounded by bound of f and things like that, right. So, we just compose G with phi. So, consider G1 to be equal to phi composed with G, okay, and then G1 works, then check that G1 works. What does that mean? Supremum over x in x mod G1 x is less than or equal to supremum over x in x mod f of x, and the set x such that f of x is not equal to G1 x has measure less than epsilon, right. Given epsilon, you can always construct a G1 in CCX such that this is true. Okay. So, let me write down one corollary to all this that will be used. Corollary, assume that the hypothesis of Lusin's theorem and mod f is less than or equal to 1, that is not really necessary, boundedness will do. Okay. Okay. Then there exists a sequence Gn in CCX such that mod Gn is less than or equal to 1 or bounded by L infinity norm of f. Okay. So, 1 because we assumed f is less than or equal to 1 and f of x equal to limit n going to infinity g n of x almost everywhere. So, you are approximating measurable functions by bounded measurable functions by continuous functions with compact support. Okay. Proof of this is immediate from whatever we have seen earlier. There exists g n in CCX such that mod g n is less than or equal to 1 because we are assuming L infinity norm f is 1 and you have sets E n such that measure is less than or equal to 2 to the n and f equal to g on E n complement, right. So, I am taking epsilon to be 2 to the minus n. So, I will have a set E n whose measure is less than epsilon and I have this equality outside that set. But sum, if I look at the sum of these mu of E n's, so mu of E n, if I look at sum of this n equal to 1 to infinity, this is finite because of this. This implies, so this I will leave it as an exercise, mu of lim sup of E n is 0. Okay. So, I will leave it as an exercise. If I have measurable sets whose measures add up to a finite quantity, then the measure of the lim sup of those sets is 0. Okay. So, for every x which is not in the lim sup, so that lim sup of E n is a set of measures 0. So, I am taking x outside that. Well, we will have f of x equal to g n of x, f of x equal to g n of x in this set. Okay. So, this will be true for large n. Okay. So, this is something you can check. So, again this is just a trivial construction, okay, and hence the result follows. So, hence the result. Okay. Well, what did we do? We are saying that for a function which is bounded, we can say that it is a limit of continuous functions. Okay. So, that will immediately tell me that it is dense in CCX. Okay. So, let us see. So, another corollary. So, we will stop with this corollary that if I take 1 less than or equal to p strictly less than infinity, LP of mu is in LP of mu CCX is dense. Okay. So, CCX is dense in LP of mu. Well, why is that? Because you can so proof is one line, approximate simple functions. Simple functions are dense in LP, we have already seen, dense in LP by CCX functions. Okay. So, I will leave the details as a simple exercise. Okay. So, we will stop with this. We have just seen that LP is a complete metric space, and if the space X has more structure, that it is a locally compact Hausdorff space, and the measure has the properties in Riesz representation theorem, etc. So, in particular all the Euclidean spaces and the Lebesgue measure there, we know that continuous functions with compact support is dense. Okay. So, we will stop here.